Okay, welcome to the introduction to section 3.7. Here we get to put what we've learned about finding maximums and minimums to the test in what are called optimization problems. So the first question here says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a maximum volume? So first thing we want to identify is what do we want to find a maximum or minimum of? So here we want to find a maximum volume, which means our first step then is to find an expression for volume. That's the thing I want to maximize, so let's find an expression for it. Okay, what else do we know about this box? We know something about its surface area. Well, that doesn't relate to its volume, but what does relate to its volume is that it has a square base. So what does that mean to have a square base? It means the dimensions of the base here would be x and x. And now to find its volume, the only other dimension I need would be the height. Well, the height is not given anywhere in our problem statement, so I will label it h. Okay, so volume of this box is the area of the base, which is x times x, or x squared times the height, which is h. Okay, there we go. We found an expression for the volume. Now, to maximize something, maximums occur, we know, when the derivative is equal to 0. But before we can start taking derivatives, the key is going to be to write this expression in one variable. Right now we have it in two variables, the dimensions of the base and the height, and we want to write it in one variable, and we should have some piece of given information that allows us to do that. And that is here, oops, we need all of it, that the surface area is 108 square inches. Okay, let's see what that can tell us. So we know the surface area is equal to 108. Well, what is the surface area? We add up the area of all 5 faces in this case because it's an open box. So the area of the base is x squared, and the area of any one of these faces, which are x by h, they have area xh, and there are 4 of those. So we have 4xh as the surface area. This is the base, and these are the 4 faces. Okay, great. So we have an expression now with a number in it that has x's and h's. So we can go ahead and solve for either x or h and then express the volume in terms of the other variable. It looks like it's going to be easier to solve for h here. So let's do that. So we get 108 minus x squared is equal to 4xh. Then we divide both sides by 4x, and we get 108 minus x squared divided by 4x is equal to h. And then we can simplify a little bit. 108 divided by 4, 4 times 20 is 80, 28 left, 7. So 27, but we still have an x in the denominator, minus 1/4, and one of the x's is going to cancel. So there's an expression for h. So now we can rewrite the volume just in terms of one variable. So now we can get the volume as a function of only x. So it looks like x squared times h, which is 27 over x minus 1/4 of x. Okay, so we can simplify this thing a little bit. So then the volume is, this looks like 27x minus 1/4 x cubed when we distribute. Okay, there's the volume as a function of just the dimensions of the base of this open box. And now we want to find which value of x will maximize. So the maximum is going to occur when the derivative is equal to 0. So we can take the derivative. It's 27 minus 3/4 x squared. We want to know when that is going to be equal to 0. 27 minus 3/4 x squared, when is that going to be equal to 0? Well, when 3/4 x squared is equal to 27, or when x squared equals 4/3 times 27, which is 27 divided by 3 is 9 times 4 is 36. So x equals plus or minus 6. Okay, so that gives us technically two choices then for x. This is the dimensions of a box, so it's not going to be negative. So we will choose x to be 6. Now the question is, how do we know if that's a maximum? Well, here's one way to decide if it's a maximum. One way to decide is to take the second derivative, uh, and let's see, what do we get? When we get the second derivative, we get 27, that derivative is 0, so we get negative 6 fourths, sorry about that, of x. Now, the second derivative evaluated at 6. I don't care what that number is, negative 6 fourths times 6. I know that that number is negative, which means that my function is concave down and that I do have a max at x equals 6. So great. So we know that 6 does maximize the volume. And so now the only thing that's left to do is answer the question. Let's see. The question says, what dimensions will produce a box with maximum value? Well, that means we need to get our hands on h. So h, if we come right up here to our last expression for it, would be 27 divided by 6 minus 1/4 of 6, so 27, 3 9/2 minus 3/2, 6/2, or 3. And so our dimensions of our box are 6 by 6 by 3. Okay, great. This is a slightly time-consuming process, but here's the way to do it. Find an expression for the thing you want to maximize or minimize. In this case, it was volume. That expression might be in one variable to begin with. Great. Go ahead and take derivatives, find where the max or min occurs. If not, if it's in more than one variable, we need to find an expression in one variable, which means we have to use given information that we have. Go ahead then and find the max or min using the derivative and or the second derivative as a tool for determining if you have a maximum or a minimum, and then go look at the question again and make sure that you provide the information that was asked for, which in this case was dimensions. Okay, let's look at a slightly different example. Which points on 4 minus x squared are closest to the point 0, 2? Okay, so let's zoom in here. We want to get close to this point. So closest to 2 means we're looking to minimize something. What are we looking to minimize? We're looking to minimize this distance, the distance to the point, some point on the curve. So let me call that distance d. Okay, so I want to minimize d. Here's the point 0, 2. Well, what's this point? I don't know, right? You're going to say, oh, it looks like it's 1, right? It is where I happen to draw it, but that's the thing I want to find. What is the appropriate x value to minimize that? So I'll just call it x, and that means it has coordinates x by 4 minus x squared, because that is our function. Okay, so if you remember the distance formula from middle school, great. Just go ahead and apply it. If you don't, just draw in this right triangle. This distance here is the distance from 0 over to x, so it's just x. And this distance here is 4 minus x squared. That's the total distance. Take away this distance from x up to this point, which is 2. It's the change in y here, which is 2 minus x squared. Okay, great. So now, where are we at? Let's redraw that triangle. I'll draw it up here. We have this triangle. This was the thing we want to minimize. This distance was x, and this distance is 2 minus x squared. And that's enough information to go ahead and get an expression for d using the Pythagorean theorem. So d squared must be equal to x squared plus 2 minus x squared squared. Okay, well that's going to tell us that d has got to be the square root of x squared plus 2 minus x squared squared. Okay, it's tempting to go ahead and multiply that thing out under the square root, but don't do it until you decide if you really have to. Now let's think about, we want to minimize this function, right? We want to minimize d. So let's think about this. What do we know about the square root function? This aside might come in handy in a few problems. So what do we know about the square root? Well, we know that it's increasing. It's always increasing. That's key. And it is continuous. Okay, what does that mean? Why might that help us? Because now I think about just the thing inside the square root. Well, whenever it's at a minimum, if it was 3, uh, the square root of 3 is smaller than the square root of 4. The square root of 2 is smaller than the square root of 6. So we really just need to minimize the thing inside the square root. And this would be the same if we were maximizing. We just have to maximize the function inside the square root. Okay, so let me change colors. I'm going to give that function a name. I'm just going to call it f of x. We want to minimize this thing, because whenever it's at a minimum, the square root will also be at a minimum. Okay, we can do that. That's not so bad. We just need to take its derivative. Again, tempting to multiply out, but just take the derivative using the chain rule. So we get 2x. The 2 comes down. We have 2 minus x squared. Then we go to 1 less power, which is 1, and then we multiply by the derivative of x squared, which is negative 2x. Okay, let's simplify this thing a little bit. What's it look like? It looks like 2x. We get 2 times 2 is 4, times negative 2x is negative 8x. We get 2 times negative x squared is negative 2x squared, times negative 2x is positive 4x cubed. So this looks like negative 6x plus 4x cubed. Okay, if we want to minimize that function, we want to know when that derivative is equal to 0. So negative 6x plus 4x cubed, we want to know when that is equal to 0. So let's see, I guess we can factor out a negative 2x from each of these terms. And it looks like we get 3x minus 2x squared is equal to 0. We could have just factored out an x either way. All right, we need to find the critical numbers of this. So let's see. Well, let's see. Clearly, this is going to give us the critical number x equals 0. And then, whoops, sorry, let's erase this x. Much better. And then we also want to know when 3 minus 2x squared is equal to 0. And I guess that's going to happen when x squared is equal to 3 halves. So x equals plus or minus the square root of 3 halves. Okay, so now what do we want to do? We have 2 possibilities for our minimum, 0 and plus or minus 3 halves. Either way, we can test either one. They're going to give us the same output. And so we want to test for a minimum, but in this case, we don't just have one. So we could take the second derivative and decide which one of these things will give us a minimum, or we could just go ahead and check to see which one minimizes f. So check for minimum. Okay, let's do that. So this thing we've called f, evaluated at 0, is going to be 0 plus 2 squared, or 4. And if we evaluate it at root 3 over square root of 3 halves, let's see, what are we going to get? We square that, we get 3 halves plus 2 minus 3 halves squared, which is 3 halves plus, let's see, that's 1 half squared. 3 halves plus 1 quarter, which is 7 quarters, which is definitely less than 4. So it turns out that our minimum occurs here. It's also going to occur here because they will give the same point, the same y coordinate. So our minimum, or the points we're interested in, are the square root of 3 halves, comma. Okay, well, we better go up to our original function then, and to find out what this point is. We know what x is, so y is going to be 4 minus the square root of 3 halves squared, which is 4 minus 3 halves, which is 4 minus 1 1/2. So that's 12 minus 3. That's, sorry, 8 halves. 4 is 8 halves minus 3 halves. So that would be 5 halves. Okay, so the points that are closest are root 3 over 2, 5 halves, and negative root 3 over 2, 5 halves. Okay, see if you can use what you learned in those two problems to work on the activity in this section.